Waalaikumsalam.
Thank you very much for the. All right, thank you very much for the response. It's very thrilling to know that you. I can still hear your voice even though it's late afternoon. Yeah, at 4 o'clock. So today we are in week 3, lesson 1, and we will be having 2 lessons this week, of course. And as you can see from the chat box, the agenda for today, we will be covering chapter 3 or topic 3 for this class. And I have uploaded the files for topic 3 in files in your class materials. And for those people who have uploaded downloaded the files earlier before I gave the announcement saying that there are slight errors in 2 slides, please refer that during the class and recorrect it on your own yourself. Yeah, if not, you can download the latest one which I wrote as updated files. Okay, so we will start the class right away with the recitation of dua. So please switch on your camera and microphone so that we can recite the dua together. You are the first one, Mr. Akasha. Mr. Afsar. Okay, the usual ones. Mesti internet laju ni kat rumah ni. Okay, please switch on your camera. Tak sabar nak puasa ni.
Puasa.
Ada siapa dah mula teropong sendiri ke?
Ada.
Ada.
Hebat.
Ada orang dah teropong ya? Siapa tu? Mashita, Najwa, Amira, Atrisha, Fazlika, Shadiana, Azian. Mereka, the ladies betulkan tudung macam depan cermin, you know. Saya pernah betulkan juga. You know, the recent viral, ada lelaki dia betulkan apa benda depan kereta. Dia tengok-tengok ada orang dalam kereta. Nur Dada, Ashikin, Tafika. Okay, I'm going to change the setting to large gallery. Fazlika, Azwan, Azri, Najwa, Amira, Mashita, Azian, Nurnada, Ashikin. Ashikin ada 2 tak, 1. Dia gerak-gerak. Afsar, Atrisha, Amani lah ya. Azri, Shadiana. Tak. Ni je ke yang buka kamera? Cerianya Syafika. Semangat. Shadiana. Semangatnya you depan laptop. Tengah tengok error saya ke? Fazlika, you mengajar tuition ke? Belakang tu pernah tulisan kat whiteboard. Wow. Business tu kat belakang kira-kira duit. There are some students who are actually ODL. They are also helping their parents, with the parents' business and so on. For those people yang tak dapat jumpa apa-apa nak buat di rumah tu, cubalah cari sesuatu ya. Pergi masak ke, pergi potong rumput ke. Ada tak rumput kat rumah? Lalang ke, bela kucing ke. You know, this ODL thing. Last year, I found one stray cat during ODL. It was in April 2020. Then I took it home. Dan sekarang dia sudah melahirkan anak dia pula. Dia bapa lah. Ciwa, dia bapa. Dia telah berkahwin dengan kucing lain. Dan kucing lain tu adalah daripada stray female cat. Female cat, kita panggil female cat lah ya. Ada special name ke? Ya, and that female cat tu stray, dia datang dah berkali beranak sejak ODL. Jadi semua tak survive, tinggal seekor je. And that seekor dah melahirkan anak sendiri, berkahwin dengan power dia lah. Berkahwin dengan kucing stray yang saya ambil di tepi jalan. You know, so those things are soothing events ya. Kalau you tak ada apa-apa nak buat, belilah kucing. Untuk anak saya yang dia stres tu, dapat kucing dia tak stres sangat. Belek-belek anak-anak kucing. So siapa yang tak ada kerja kat rumah tu, kalau dah penat membaca tu, pergilah tolong apa-apa, whatever that you want to do. Now, very good. So I see all your faces. Nampak kat sini very ceria even though at 4 o'clock. So we are going to recite our doa. Ada siapa nak lead the doa? Doa pembuka? Any volunteer? Other than Mr. Akasha? Ada tak? Ada siapa yang lain? Tak ada? Okay, Mr. Akasha, the floor is yours.
Alright.
Okay.
أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم الحمد لله رب العالمين حمدا يوافي نعمه ويكافئ مزيدا يا ربنا لك الحمد كما ينبغي لجلال وجهك الكريم وعظيم سلطانك اللهم صل على سيدنا محمد وعلى آل محمد اللهم اغفر لنا ذنوبنا ولوالدينا وارحمهما كما ربيانا صغيرا
Ya Allahumma ja'alni fi qalbi nura
وفي
wa fi
لساني
lisani nura wa fi basari nura
وفي
wa fi sam'i nura wa
وعين
yamini nura wa
وعين
yasari nura wa
ومن
min fawqi nura wa min tahti nura wa min amami nura wa min khalfi nura واجعل لي في نفسي نورا رب اشرح لي صدري ويسر لي أمري واحلل عقدة من لساني يفقه قولي اللهم افتح علينا حكمتك وانشر علينا من فضائل رحمتك يا أرحم الراحمين.
سبحانك ربك رب العزة عما يصفون وسلام على المرسلين والحمد لله رب العالمين.
Amin, amin, ya Rabbal Alameen. Thank you to Mr. Akasha and also everyone for your cooperation. Yeah, so we will start our class right away. I will share my slides and you may switch off your video. Okay, can you now see my slide?
Yes.
Yes.
All right, very good. Okay, now we are in lecture topic 3 and we will still be using the textbook Fogler and Levenspiel, and the content that I will be using, I will be referring to my lecture today is 4th edition and some of them a little bit from the 5th edition. Yeah, I will mention about it. And also Levenspiel. So this is topic 3. We have 2 parts, part 1 and also part 2. And today we will cover part 1. If we have enough time, then we will finish part 1. If it's too heavy, then we will stop at where we think it is most appropriate. Yeah. So it sounds like it's kind of heavy lecture today, but not so difficult. Yeah. All right, so you see on the slide here, we have topic 3 and topic 4. Topic 3 is what we are going to do this week in week 3 and topic 4 in week 4. The first 3 topics, subtopics are from topic 3, which are stoichiometry, material balance, and the relationship between the concentration and the conversion. Yeah, so we will do this once we know how to form our stoichiometric table when we write our material balance. The rest will be covered next week under the ideal reactors for single reaction. So basically all of them are very crucial for the design of the chemical reactor. Now, before I start into the theories of topic 3, I always like to show the summary of the whole topic so that you can visualize what's coming. Yeah, for example, this is only the summarized points that we have learned from the past 2 weeks, which is very common to you already, which is the reaction equation involving the two components producing, which are A and B, producing C and D together with the stoichiometric ratios based on the A 1 mole of A, or we call it as per 1 mole of A, if we assume the A is as the limiting reactant. Yeah. Okay. And the second equation is simply the relative rates of the reaction based on the rates of the disappearance of the reactants and the rate of the formation of the products divided by the stoichiometric values from the main equation. Now, this slide also is a summary of what you have learned earlier, showing you the power law model equation consisting of the temperature-dependent term, which is the rate constant, multiplied by the results of two multiplication between the two components, two reactants, which are the concentration of A and concentration of B, with the power to its respective order of reaction, alpha and beta. So alpha refers to the order of reaction with respect to A, and beta refers to the order of reaction with respect to B. Okay, this slide shows you mainly about the Arrhenius equation. So we know that we have two kinds of K, the small k, which is the rate constant. The capital K is the equilibrium constant for a reversible reaction. Yeah. The first one is simply the Arrhenius equation having the activation energy, the R, which is the universal gas constant, and the T is the temperature of the operating condition. Then the A is simply the pre-exponential factor, or in this case, it is called as frequency factor. Then if we were to compare between two temperatures, knowing the temperature of a specific condition, so we can find the rate constant or also the equilibrium constant at a specific temperature, knowing the temperature of the other condition, the rate constant, and also the temperature. And for the equilibrium constant, knowing the heat of reaction, which is this delta HRX, yeah, that is the heat of reaction. And also knowing the other temperature, okay? So this is what I mentioned earlier that I took from the 5th edition. Even though I wrote here 4th edition, the contents are actually the same, yeah, 4th and 5th. It's just that how it is being represented. It is much more improved in the 5th edition, whereby we have concept 1, 2, 3 elaborated here, yeah, showing concept 1 saying that the rate increases with the increasing reactant concentrations. Yeah, let's say if you have two reactors, this is just to elaborate. The concentration of A, of course, both also having the same reaction, but just to compare the CA1 and CA2, yeah, let's say CA1 is not the same as the CA2, but with a constant temperature. So therefore, the rate A and the rate A here for 1 and 2 also differs. So it says here the rate increases with the increasing reactant concentration, meaning as the initial concentration of the specific limiting reactant is higher than the other condition, then you should expect that the rate of reaction for the higher concentration of delimiting reactant is much higher then. Yeah, it's proportional to the increasing temperature concentration. The concept 2 says that the rate is related to the potential barrier height and to the conversion of translational energy into potential energy. So this is much related to what's going on inside the reaction mixture where we have the reaction. It is related to the translational energy into potential energy, producing the products. Concept 3, the rate increases as the fraction of collisions that have sufficient energy to cross over the barrier and form product increases. So those two concepts, 2 and 3, are the detailed explanation of the fundamental occurrence, yeah, when chemical reaction occur. Okay. Right, this slide is what you will be seeing, yeah, in this topic 3, mainly on the chemical flow or the flow reactor design, yeah. So in this topic 3, we will be having 2 kinds of system, batch system or the flow reactor system. Hold on a second. I hear some voices. Can Miss Amira switch off your microphone? Miss Amira? Miss Amira, can you switch off your microphone? Now it's better. Yeah, I hear some windy noises. All right. Now, so we are here. So this slide shows you the stoichiometric table, but this is more towards the flow reactor design. But before we do this stoichiometric reactor table, stoichiometric table for flow reactor design, we will start doing the same thing for the batch design, yeah. But at least you know that for a stoichiometric design, we will need to first to identify the species, either the reactant or the product, and also we have another new word maybe for you, inert. Yeah, in this case, in some reactions, inerts are added, but there are no changes for the inerts. That is why it is called inerts. So that's why for the inert we have no change there. Yeah, the rest we simply write as the symbol used for entering, and then what's going on inside, the changes, and what's leaving. Okay. And finally, we will write the total formulas. In this case, F refers to flow rate. Yeah, the unit is mole per unit time. We will further look into that in the next slide. This is just an overview. Now, in this topic as well, you need to expect that when we have batch design, a batch reactor, when we run our reaction in a batch reactor, the assumption that you have to use or you may use is a constant volume. In this case, the volume is considered to be the same throughout the time, since the reaction mixture volume is considered to be constant as V naught. V naught would refer to the initial temperature, the initial time, yeah, T equals to 0 hour or second or whatever. And the other part that is also being covered in topic 3 is flow reactor system in gas or liquid form, yeah. So if it's in gas, then we will use this symbol. In Greek letter, we call it upsilon. And that upsilon refers to the volumetric flow rate. Volumetric flow rate. And for liquid, we also use the same symbol, upsilon. And for liquid, we can assume that the volumetric flow rate is considered to be constant, but it is not for the gas form. Yeah. Here, the varying volumetric flow rate is seen with the influence of the pressure, and of course we have the temperature reference there. Then you will also see two different new terms that you will be seeing, which are delta in Greek letter word and epsilon. The delta is the change of total number of moles per mole of air reacted, and the epsilon is the change of total number of moles for complete conversion over the total number of moles fed to the reactor. Yeah. So those two symbols, you will see that in the stoichiometric table later on. Yeah, this is again another few summarized formulas that you will be seeing as the conclusion from our lesson in topic 3, based on first the for incompressible liquid, second for gas phase reaction. So therefore, it means that you should be expecting to learn how to balance the equation for gas phase reactions, yeah, in a reactor with certain assumption, and also incompressible liquid, especially when you have this liquid in a constant volume, assuming volume is equivalent to the initial volume. Yeah. So those are the few equations which we will be seeing as the conclusion out of the derivation or the fundamental theories. S for 7, S for 8, and S for 9 and 10 are the formulas for the concentration of the components in gas phase reactions. Yeah. Take note that we will be using certain simple formulas as starting to write the theories. Yeah. For example, you could see this is a very common, which is the concentration of any species is equivalent to the feed rate or the flow rate per unit. This one is volumetric flow rate. Yeah. Same goes to, we have earlier in a batch system, the C is equivalent to N over V. If it's A, then NA over the volume. Yeah. So that is also another common equation that you may want to remember, right? You will also see another symbol there, theta, but we will further look into that once we are in the slide. All right, in the 4th edition, but I don't see this in the 5th edition, we have this kind of overall overview of the equations related to topic 3. Yeah, take note that in 5th edition, in topic 3, 4th edition are mainly from chapter 3, yeah, in Fogler. But in 5th edition, Fogler, the topic 3 is now found in chapter 4. Yeah, they just rearrange the numbering of the chapters, but mainly they are having the same contents. Yeah. So I still share this one from the 4th edition, showing you in case if you have this kind of the example of the chemical reaction dealing with two components, A and B producing C and D, you should be asking yourself, the reaction occurs in a liquid phase or gas phase. If it's liquid phase, then you will follow series of equation, or the assumptions are different. But if it's gas phase, then it will follow certain assumption based on certain fundamental theories. Yeah. So take note. So we will learn this slowly, one by one. And of course, for both phases, liquid and gas phase, you will be asking yourself also whether you run your experiment or your reaction in a batch system or a flow reactor system. So the question would be, what is flow reactor system? Yeah. The batch is simply, you know, that we have a fixed volume, so we have no continuous inlet and outlet. But the flow is simply we have continuous inlet and outlet with the F in and the F out. Yeah, the inlet flow rate and the outlet flow rate. Yeah. In this case, the unit for the F is mole per time. Same goes to the outlet, mole per time. The other word that we use here is molar flow rate. Okay. But of course, in batch system, we don't have the inlet F. We don't have that. Outlet F, we also don't have that. Yeah, it's simply the batch system. So that will be the difference. Okay. Now, let's start with the introductory of the stoichiometric table itself. What does it mean? Yeah, the stoichiometric table represents the stoichiometric relationship between the reacting molecules for a single reaction. So in this topic 3, we will be looking into single reaction, and we want to relate the stoichiometric values from one reactant to the other reactant to the product. So basically, this is what you're going to vision or you're going to expect to be doing, yeah, writing the stoichiometric values accordingly. And it also refers to the relative rates of the reaction. Simply by writing the reaction equation, it will represent the batch reaction, for instance, for a batch reactor. Yeah, meaning if you know that you are running the reactions in a batch system, then you write the equation, or we call it general reaction equation, accordingly to a batch system, yeah, following certain fundamental understanding. Yeah, you will see about that in the slide later on. Then finally, you will need to formulate the stoichiometric table, formulating the formulas based on the limiting reactant. Yeah, take note, this is again another error which I forgot to recorrect it. Reactant, not reagent. Based on the limiting reactant. Yeah, if you say A is the limiting reactant, so we will write the stoichiometry based on per mole of the limiting reactant. Yeah, if it's A, then A. Then, of course, in this topic, we will cover the stoichiometry and the relationship between concentration and conversion for batch reactor system and flow reactor system. All right, so this is taken from our previous slide last week, the relationship between the conversion where you have the X in the equation of moles of A reacted. Yeah, how much A being reacted in the reaction depends on the initial value of the number of moles of the A times the conversion. Yeah. And the moles of A at any time is simply, how many moles of A at any time is simply the initial number of mole of the A minus the reacted moles of A, yeah, having with the influence of the conversion, of course, right? So you can see that in this equation, which was learned last week, the definition of the X, and also how we write the equation for the moles of A at any time, yeah? Initial minus the reacted A. Of course, don't forget to also remember that the change of number of moles of certain component through time in a batch reactor system depends on the rate of reaction times the volume, yeah? In this case, if we are dealing with batch reactor system, then the volume is considered to be constant. So V is equivalent to V naught, for example. All right. Let's say if we use this batch reactor system, so what happens in the reactor itself or in the reaction mixture? So at time 0, the number of moles is considered to be N naught. Yeah, I refers to a particular reactant. If it's A, then N A naught. Yeah, it refers to the number of moles of A at initial time. So we also write as Ni or Na at any time T. Yeah, so this is what you're going to see in the reaction mixture. Of course, we have C and so on. Yeah, the C, the concentration of the reactants and the products. Now, the question would be, what is the total number of moles of A reacted? Right? Before this, we look into the number of moles of A, which is the limiting reactant, reacted. But if we were to write the number of moles of B reacted, it depends still. We refer to the limiting reactant per mole of the limiting reactant. So A is per mole. Therefore, we have these stoichiometric ratios for each of the component. So to write the moles of B reacted is simply how many moles of the B over the moles of the A times, this is basically refers to the stoichiometric, Mm, the, 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 the value of the stoichiometry here, B over the A. So B over A refers to how many moles for the A, how many moles for the A, using the stoichiometric values of A and also the B, since we refer it to per mole of A, times the mole of A reacted. So this is what you learned earlier, simply the initial number of moles of the A times the conversion. So therefore, moles of B reacted is referred to how much of the A, initial A, being converted times the stoichiometric ratio needed for 1 mole of A. All right? Meaning to say, whatever moles of B reacted depends on this initial value being converted. Times the stoichiometric ratio. All right. The other one would be, what is the total number of moles of B remaining? Here is number of moles of B reacted. How much is being used? How much is being used here for 1 mole of A? But here is how much of the B remaining, meaning knowing how much of the B reacted, we can know how much of the A remaining. So how to write that? The number of moles of B remaining is simply, of course, if we know the initial mole of the B, we simply use that as our reference minus the number of mole of B reacted. Simply write this understanding as the number of mole of B at any time, T at T is equivalent to initial minus the number of moles of B reacted, which is taken from the previous slide. So before I proceed with the stoichiometric or the stoichiometry, does anyone have any question that you want to ask me before I go further? Yes, Shafika?
No, doctor.
Okay, very good. Now, so we are going to start to write the stoichiometric table. There are 3 steps. First, by forming the columns. Secondly, in the columns, we identify the inerts. If there is no inert, then you don't have to write inerts there. Then finally, formulate the total number of moles. So what does it mean by forming the columns? There are 4 kinds of column, as you see here. Column number 1, 2, 3, 4. So number 1 is simply the components, A and B as the reactant, C and D as the product, and then we have I as the inert. Initial, column number 2 is initial. Simply write the formula for initial. In this case, batch, then number of mole of the species. And A naught. Naught refers to when T equals to 0. And B naught, and C naught, and D naught, and I naught. Then change means what happens? Change. This simply means the number of moles reacted, correct? Change. Is that true? If you still remember our previous slide, the number of moles Mana dah? Reacted. Betul lah tu. Alright. A. Same goes to B. So we have A minus, meaning of course we need to deduct it because it's disappearing. Then B disappearing. Then product C plus. It means the number of mole in for this case it is not reacted. Number of moles formed, right? Based on per mole of A. Same goes to D, the number of mole formed. So the change would be either disappearing or forming. Yeah, moles of disappearance or moles of formation. Then the fourth column is simply remaining. So remaining is easy, initial minus whatever happening, disappearing or initial plus forming. For the C, initial plus forming for the D. Okay. Since inert has no change, then the initial is equivalent to the remaining. And finally, you formulate the total number of moles as shown here. All right. So we can also write the total number of moles based on delta. So what is delta? Delta is change in total number of moles per mole of A reacted. So simply initial, the total initial, we have the number of mole total initial minus the delta times the Na naught X. Yeah. The number of mole initial times the conversion. And we can also write the stoichiometric table based on concentration. Yeah, this is what you see earlier based on the number of moles. And we know that concentration can be written in terms of number of moles per volume. If it's Ca naught, then Na naught over V naught. Yeah, Cd naught is Nd naught over V naught. But the common formula for the concentration, of course, simply Ca and A over V, Cv and V over V, Cd and D over V. Here, we just need to replace the formula for the number of moles of A at any time based on that initial minus reacted. Yeah. Same goes to here. NB initial minus reacted. ND initial plus formed. C and C not initial plus formed. Okay. Right. In the stoichiometric table, we can also not only express in terms of number of moles and concentration, we can also express this in terms of theta. So the question would be, what is theta? Theta is simply the ratio of the initial number of mole to the initial number of mole of the limiting reactant. If we write theta in terms of concentration, it is simply the concentration initial of that component over the initial concentration of the limiting reactant, which is dA, right? So we have this equation earlier, the one that we have seen from our previous slide. We are now going to convert this in terms of theta using this principle. Yeah. If we have n, then we will use the first principle, which is the ratio of the n. So how to do that? So we have, if it's theta A, then the equation for theta A is Na naught over Na naught. Yeah. If it's theta B, then NB naught in reference to Na naught, right? So that is theta B. So let us have a look at this equation for B. So we'll go to the next slide. It should be written clearly, but anyway, we can do that here. We have this NB, and how to relate that to here, theta B. Since theta B is NB naught over the Na naught, so what we can do is divide this by the Na naught, yeah, and times this by the Na naught. then we can simply cancel that out. Then it will give you theta there. Yeah, MB naught over NA naught. And that is seen in here. Because this one also NA naught. Okay, you can see that clearly here. It becomes 1. Then we have theta here because this is NB naught over NA naught. Simply cancel that out. It will give you the original equation. Same goes to the other term. Yeah. The point is to re-express each of the equation by giving you the same meaning, but now we have the expression theta in the equation. So we don't want to change the definition of the equation, but simply rewriting it in terms of theta. All right. So this is what you see by introducing theta in the stoichiometry for each of the concentration equation. All right. But if you don't understand, please stop me. Yeah. If you just keep quiet, then I will go further to the next slide. Even if later on you think that you want to ask questions, just stop me anytime. Okay. We can just go back to the previous slides. It's okay. Don't worry. So now, when we are dealing with the batch reactor system, the assumption that we want to make is definitely the volume of the reactor system is constant. So therefore, you write V equals to V naught. So how are we going to relate this in the stoichiometry equations? Yeah. For example, here we have CA is equivalent to NA over V. Yeah. If you go back to earlier, we have CA is equivalent to NA over V. But now since we say V is V naught, then it's written as such. Yeah. Everything is per V naught. So how are we going to use this per V naught to another relationship of C? Yeah, we will go to the slide later on. But this slide just showing you the equation can be rewritten when we assume V equals to V naught. Now, we want to ask ourselves, what do you mean by constant volume? So we have 3 kinds of scenarios which illustrate the constant volume condition. Yeah, the first one, if it is a sealed constant volume vessel with an appropriate instruments to measure the PNT, meaning at that pressure and temperature in a sealed constant volume vessel, then you can say the reaction is operating in a constant volume condition. For a gas phase isothermal reactor, if the reactor is set to be at constant temperature, isothermal reactor, for a gas phase, so we can say the number of moles of the reactant is equivalent to the number of moles of the product at that specific temperature and pressure. The third one is the liquid phase organic reactions. Most of it do not change its density, meaning for a constant volume, it means constant density. Yeah. So that is why all the equation that you have, NA over V now becomes NA over V naught, just to rewrite the equation showing a batch reactor system with a constant volume. So this is the same table. So we'll skip to the other one. Now we want to re-express the equation. We have the left-hand side as concentration, the right-hand side with the N and also V. What happens if we convert NA over V as C? Yeah, knowing C is equivalent to NA of N over V. So we can do that. So look at that, NA over V, NA over V, NA over V. So we can re-express that as NA naught over V naught. Now it is defined as CA naught. So we write CA naught for each of the equation. So what can you see here? It means the concentration of A depends definitely on the initial concentration of A. Yeah. Same goes to B. The concentration of B also depends on the initial concentration of A, yeah, saying that the A is the limiting reactance. Of course, it is multiplied by the theta and also what is consumed, right? The concentration of C also depends on the concentration initial of the A, because we say the A is the limiting reactant. Yeah, for each mole of the limiting reactant, how much C is being formed, how much D is being formed, how much B is being reacted, how much A is being, yeah, of course, A, then CA, right? So that is done with the with the batch reactor system. Do you have any question before I go to the flow reactor system? Or you want to take your first 5 minutes break?
Yes, Doctor.
Alright, tadi suara ceria, sekarang dah tak ceria dah karya. Yes, betul letihnya. So go to your kitchen and take some water. Today may be your last day boleh minum-minum dalam kelas. Esok lusa dah tak boleh. Kalau esok puasa dan tak boleh lah minum dalam kelas ya. Tiba-tiba kantor pula minum dalam kelas masa tengah baca doa. Alamak. Alright, so let's take our first 5 minutes break, yeah?
Okay, Doctor.
Okay, Doctor.
Thank you.
Okay, Doctor.
Assalamualaikum. We are back. Are you still there?
Waalaikumsalam.
Jom kita makan dulu. Saya mengantuk. Saya mengajar pun boleh ngantuk. Macam mana?
Ya doktor nak ambil aiskrim.
Ha, jom. Jom buka gambar, jom tengok. Mana skrim you Afsar? Makan plum.
Bau je habis doktor.
Alah. Lain kali ajak lah makan sekali. Lah, sedapnya. Kena kat rumah boleh ada aiskrim kon. Selalu kat kedai je ada aiskrim kon.
Dah beli awal. Masuk puasa.
Betul. Baru nak cakap. Ni sebab nak puasa lah ni, makan siap-siap dalam kelas. Lepas ni kot silap kantor kan. Malu saya. Okay. Patut ni kita buat bacaan tahlil ke sebelum Ramadan ni, kita buat tak apa party pula. But anyway, so let's start. Tadi kita kat mana? You can still see the slide, right? The PowerPoint slide.
Yes. Yes.
Very good. Kalau lambat jawab tu mesti tengah makan tu. Alright, so we are now in a flow reactor system for a stoichiometry. What is flow reactor system? You have seen earlier, I sketched the flow reactor system. The example of flow is CSTR, PBR, which is the packed bed, PFR, which is the plug flow reactor or the tubular reactor. And for each of these examples of the flow reactor, definitely for batch system or flow reactor system, we have to write the general mole balance according to the respective system. If it's for flow reactor system, then write the mole balance for flow reactor system. Then of course, after that, you write the stoichiometric equation, yeah? Now, so these are the examples of the flow reactor system, whereby we have the inlet flow rate, we have outlet flow rate. Yeah, the schematic. This is a very simple schematic diagram. Yeah, you have inlet, then you have outlet, and these are the assumptions that we can use for a flow reactor system. If we are using CSTR, which is continuous stirred tank reactor, then it's mainly suitable for a liquid system, liquid phase system. Then we can make an assumption that it reaches its steady state, yeah, because we want to simplify things, we can solve certain findings or determination based on steady state so that it's much more simplified, not so much complex. And if we have this impeller thing, the impeller is meant to mix the reaction mixture homogeneously. Therefore, it reaches its ideal stirred, continuous ideal reactor, ideal CSTR, which is assumed to be perfectly mixed due to the impeller or agitator. When this happens, the concentration, I want to erase something, hold on. The concentration at any position, I cannot. Hold on, I want to erase something. I want to erase this one. All right. The concentration at any position when it's perfectly mixed, homogeneously mixed, the concentration, the R, at any position are considered to be uniform, yeah? Meaning there is no spatial variation in the rate of reaction at any position, yeah, in the reaction mixture. And there is no time dependence or position dependence of the temperature, the concentration, and also the R in CSTR. Meaning at any position, at any point in the reaction mixture, the temperature is considered to be the same or uniform due to the homogeneously mixed condition by the impeller. Once you know that you are dealing with the flow reactor system, we will start to write the mole balance, yeah, the mole balance equation based on this specific rule, yeah, showing that rate of flow into minus rate of flow going out plus rate of generation of that species in the reactor is equivalent to the accumulation rate of the system. Whereby, since we have this CSTR, we have inlet, yeah, whatever comes in minus whatever comes out, yeah, the flow rate coming in minus the flow rate coming out plus the rate of generation inside plus whatever happens inside, yeah, which depends on the rate of reaction and also the volume, right? Here we have dV because we are talking about flow reactor system whereby the V is not considered as V naught, yeah, it's not a constant volume, yeah. And the rate of accumulation on the right-hand side is simply the change of mole per unit time. So that will give you the rate of accumulation. So here from this mole balance equation, we can solve for time needed in a batch system, whereby if you want to know how much time needed to reach certain conversion, then we simply write the mole balance equation, then solve for the conversion, for example. We can also find the reactor volume values for a continuous flow. Since we have continuous flow, so what is the reactor volume suitable for that CSTR at certain conversion needed? Yeah, so that can be done by first writing the mole balance equation. Now we are going to simplify the mole balance equation based on our assumption. So what is our assumption? Mainly start with the steady state. We know that the rate of accumulation, meaning the number of mole keep changing. If it reaches its steady state, so therefore there is no longer changes, yeah, in the rate of accumulation. So therefore you can say the number of mole per unit time is equivalent to 0, yeah. The right hand side is now 0. So what is left is only the left hand side. And it is kenapa batuk pula ni? Bismillahirrahmanirrahim. Dia suruh minum air. Minum. Hari ni saya dengan secara rasminya meminum air. Nak cerita. Coklat susu setelah beberapa minggu. Konon-kononnya nak diet tapi kecundang hari ini sebab mengingatkan esok puasa. Contoh. So hari ni kita cheat day. Jom cheat day. Tapi jangan cheat masa Ramadan, berdosa. Hari ni tak apa lagi. Kat mana saya tadi? So we want to simplify the equation. Other than the steady state assumption on the right hand side, we can also simplify the third term if we assume it is perfectly mixed. When it is perfectly mixed, the R everywhere is considered to be the same, yeah? So you integrate based on the R and the change of volume. So therefore can be simplified as the volume times the R, all right? Now, having that equation, so we cancel that out. We simplify this to here. Then we have that simplified equation. From that equation, we can define volume for that CSTR. The volume is simply the flow rate inlet minus the flow rate outlet over the rate of reaction. Yeah, minus rate of reaction, which is the rate of disappearance of certain component. Now, please also remember how to write the flow rate. In this case, since the F, whatever comes in is in mole per time, so we call it molar flow rate, can also be written in terms of epsilon, which is volumetric flow rate, yeah, which is volume per unit time. Yeah, volume per unit time is like cubic meter per hour, let's say. So that is volumetric flow rate. So the F, the molar flow rate, can be written as concentration, which is mole, this one, mole per volume, yeah, concentration times volume per unit time, yeah. In this case, mole per meter cube, then meter cube per time. So simply cancel that out, then you get mole per time, which is equivalent to molar flow rate. So please also know how to write this molar flow rate formula in terms of concentration and the volumetric flow rate. Now, having said that, we simply replace the F based on C and epsilon. Then if it's not, then simply you have epsilon naught, then CA naught. Okay? Here we don't have naught, then you don't need to put the naught. Simple. Right, so this is the example of tubular reactor, which is plug flow reactor. What do you mean by plug flow? We have one whole stretch of pipeline tubing. So we have inlet, then it comes out at the end of the pipe. Yeah. So this is a tubular reactor. So if you were to take one small section, zoom it, then we see the figure 110. Yeah. This is the zoom section of the tubular reactor. Means if saying that whatever comes in at that boundary will go out at the other short boundary as well. So this is the inlet flow rate. Then it goes through another section. Of course, that section, you imagine your section because you want to write the conservation of equation or the more balanced equation based on the small section. Yeah. So we have the inlet, then we have the outlet at delta V. Yeah, with varying volume. Yeah, this volume. Can also be expressed as whatever comes in is firstly the reactant, and whatever goes out is definitely the reactant is being now converted into products. Yeah. Okay, so this slide is quite important to understand two things. Yeah, the first one is axial variation. The second one is radial variation. Lebih dulu. Okay. The radial variation is considered to be constant. Yeah, no changes in the radial variation, but there is varying values of changes for the axial radiation. So, what do they mean? For the radial radial variation, radial means if you take one slice, whatever slice. So we have many slices. Yeah, we call it, this is position 1, position 2, 3, and blah, 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 blah. So let us say if we only look at one slice. Yeah. So we have this diameter for at any point at that slice has no variation of C or R or T or whatever, the V. Okay. Meaning at any point radially, the C stays the same. Okay. But then if you compare at any point in position 2, also C, R, T, V, they are the same at point 2. But the C at 2 is not the same as C at 1. Or the rate at 2 is not the same as the rate at 1. Right? So the axial variation refers to the varying values as it goes axially. Yeah. Let's say kalau ini inlet dari kiri, then as it goes left to right. Alright. So for different position, we'll have different C's, we'll have different R along the tubular reactor. So that is variation axially. But in one position radially, it is uniform. Kira lah kat mana radially, as long as it's at the same radial direction. All right. Do you have any question before I go to the next slide? No? Okay, so thank you, Hanani. We'll go to the next slide for a tubular reactor, knowing the mole balance equation. Then since this is a flow reactor system, we can say that the change of flow rate per unit volume yeah, per volume is equivalent to the rate of reaction. Yeah. And we can also, not to say we can also, but that is, remember for a batch system, we say, okay, I'm going to go to that slide. We say that for a batch system, yeah, the change of number of moles is equivalent to RAV. Okay, that is for batch system. But for flow system, not the change of number of moles, but the change of flow rate, right? The change of the flow rate of the component per the change of volume is equivalent to dr. Okay, in this case, dFA is equivalent to RA dV. All right. Then we have the flow reactor system, we have dV. For batch system, we have dNA over time is equivalent to RAV. Okay. But for flow is dFA is equivalent to RAdV. So that would be the tubular reactor. And other basic equation considering the air for a flow reactor system is molar flow rate at which A is fed to the system, which is FA0 inlet, minus molar flow rate at which A is consumed, yeah, the FA0 times dx consumed. So this is consumed, molar flow, molar rate. This is molar flow rate. It's the same thing, yeah, since multiplied by the conversion, but here is consumed. Is equivalent to molar flow rate at which A leaves the system. Okay, so you have this one section. We have FA0, then we have FA. Yeah, whatever happens here is the changes, which is minus FA0 times dx. The initial, how much the initial of the A times how much the A is being converted, which is dx. Yeah. Now, that can be written as the FA0 times x. This is the definition of the x. This is the FA0, right? You can simply write the equation accordingly. Okay. What else? Of course, please remember this. The molar flow rate is in the function of concentration and also the epsilon, which is the volumetric flow rate. If we have not, then the whole thing got not as well. If we don't have not, then there is no not, there is no not, there is no not. Now, this slide shows you the basic design equation again for the flow reactor system, but we are going to relate it to gas system. For example, using the ideal gas law. And you know this is the equation for ideal gas law, and you know that N over V is C. If you rearrange that, so C is equivalent to the partial pressure of that component over the universal gas constant times the temperature. If it's not initial, then everything is T naught initial, then partial pressure A naught, yeah, partial pressure of the species at initial time. Of course, R stays the same because R is ideal gas constant, right? So the molar flow rate initial can also be written in terms of partial pressure and also the RT accordingly to the ideal gas law. This is simply re-expressing it. But then we have this Y. So the Y refers to the entering mole fraction, the YA naught. If we are referring to naught, it means the entering. The entering mole fraction of the A times the partial pressure, P over RT, yeah? P over RT, the partial pressure, and also the epsilon, which is the volumetric flow rate initial. Okay. Right, so where does this comes from? I just want to show you, it comes from here, of course. The partial pressure initial is equivalent to the mole fraction in gas. The Y is always the gas mole fraction times the partial pressure, yeah? P naught, entering total pressure. entering partial total pressure, entering total partial pressure, something like that. Okay, what else? Okay, for liquid system, of course, you use concentration. For the symbol C, for the gas system, it's still concentration, but it is being represented by the partial pressure. Now, here is the illustration of the stoichiometry having the entering flow rate, molar flow rate, and the leaving molar flow rate for a flow reactor system. Yeah, and again, this is the example of writing the stoichiometric table for a flow reactor system, having the same steps whereby you write the species, identify the species, the two reactants, the two product, the inert, then the initial, yeah, we have the initial FA naught, FB naught, FC naught, FD naught, FI naught. Then we have the change, whatever going on inside, either disappearing or forming. Okay. Then the remaining, yeah, the effluent rate from, in this case, the effluent rate, which is coming out from the reactor, yeah, the leaving. The effluent means leaving. Effluent means leaving. So the other words for entering is influent. We use it as entering or inlet, yeah. If you say effluent, that it means the leaving stream from the flow reactor. So the effluent rate is simply the initial minus the change. Yeah, so you do that for each of the condition. Take note for the reactant. Of course, we have the minus because it means the disappearing moles or the disappearing rates. For product, we have plus, yeah, deforming rates. All right. Now, for the flow reactor system, we can write in terms of molar flow rate and also the epsilon, which is the volumetric flow rate, and relate it to the concentration. Here, simply rewrite this FA, FB, FC, FD in terms of the A naught, yeah? So B naught, C naught, D naught, yeah? And also because those are referring to the initial minus changes, yeah? The changes depends on the conversion and also the initial of the limiting reactant. All right, so these are all same thing as the batch reactor system. When you write your stoichiometric table, remember in batch reactor system, we have this as volume, yeah, in batch. But for the flow, instead of volume, we use volumetric flow rate, which is the epsilon. So that is why you see epsilon there. So we are going to introduce another symbol there, is what I told you from the beginning, which is theta. Theta is simply, okay, if it's theta B, then FB naught over in reference to A, okay? Then simply re-express the flow rate, molar flow rate in terms of concentration and volumetric flow rate. Then simplify that. Then you'll get theta also is also defined as the ratio of that particular species at initial time to the limiting reactant concentration at initial time, right? Can also be written as the ratio of the mole fraction of that species at initial time per mole fraction of the limiting reactant at initial time. Can you still absorb more information? Ataupun you nak relax dulu, nak cuba tulis sendiri? Sebab dah petang ni. Ha? Ataupun terus nak buat example 3.2. You still want me to continue? Tinggal sikit je lagi. One slide je. Boleh? Can we still proceed?
Boleh,
Boleh, ya?
doktor. Boleh.
Boleh.
since you have the PDF, so I think it's not so difficult kalau you nak tengok-tengok ya. Now, so here we want to refresh our understanding on a batch reactor system. Like I told you, for the batch reactor system, we refer that to volume, yeah, volume. Then we express that in terms of theta when we assume volume is equivalent to V naught, yeah, but volume is equivalent to the initial volume. And we also re-express that NA over V naught in terms of CA naught, yeah, we do that. For the flow phase, we also can express that in terms of theta, whereby we divide each term by the upsilon, which is the volumetric flow rate. So once we do that, we also have this theta B, theta C, theta D in the equation of the flow rate. Yeah. This is done as what we have been doing here, whereby we introduce NA naught, yeah, introduce NA naught to each of the term, yeah, so that we can use the definition of the theta. So we do that as well for the flow reactor system. Okay, so that would be the examples that I recommend you to have a look in 4th edition 3.2 and 3.3. I haven't looked at the 5th edition, but you can try first with the equation 3.2, whereby it's an example of a soap consisting sodium and potassium salts with various fatty acids, oleic, stearic, palmitic, lauric, and myristic acids, with the assumption of the volume is equivalent to the initial volume. Yeah. So when we want to produce soap, then we use the saponification principle, whereby we use aqueous caustic soda and also glycerol stearate. Yeah, so we have caustic soda, which is the sodium hydroxide, and glycerol stearate is a source of glycerin. Yeah, oil. It can be from oil, and from the saponification process, it produces soap, and finally glycerin. So now the question asks you to assume if X, yeah, is the conversion of the sodium hydroxide, which is the number of moles reacted per moles of the sodium hydroxide initial present. Let me see what is the question. Letting X represent the conversion of sodium hydroxide reacted per mole of sodium hydroxide initially present, set up a stoichiometric table. So it asks you to set up or form your own stoichiometric table expressing the concentration of each species in terms of its initial concentration and conversion X. Yeah. So you use this definition of X, you know the definition of X. We are saying, yeah, the question says, the sodium hydroxide as the limiting reactant. Is it true? Yeah, it says that conversion of the sodium hydroxide, moles of sodium hydroxide reacted for moles of sodium hydroxide initially present. So please form this stoichiometric table. You can try that on your own, or you want me to bring you to your breakout room? Do you want to discuss it with your friends? Siapa yang nak buat sendiri-sendiri? Macam mana?
Tak kisah doktor, mana-mana pun boleh.
Mana-mana? Okay, kalau macam tu saya bagi breakout room lah. Jumpa kawan-kawan you. Okay. How many students we have? 28. 9 lah. Ada 2 guys. Boleh lah. 9 groups. Okay. 6. 9 group. 8 rooms. So I'm going to start the room now. But I will jump from one group to the other group for the remaining 20 minutes, yeah? All right? So you may start to get to know each other, then discuss, relook at the notes. Maybe it'll take some time for you to write your stochametric table, but at least you start to discuss with your friends, yeah? So do refer to your PDF form, the PDF slide, yeah? Lecture notes. So the room is starting. Syafika, tak dapat masuk breakout room ke?
Doktor, saya punya laptop tiba-tiba restart. Lepas tu saya masuk balik guna iPad. Lepas tu tak ada pun backup saya.
Oh, you tak ada assign eh? Sekejap. No, Syafika. Mana nak add kamu ni ya? Sekejap, macam mana nak add siapa yang lambat ni? Okay, dia apa dalam room 9 ni? Tunggu Syafika. Dalam ni mana nak add ni? Sekejap Syafika. Mana nak add Syafiqah ni? Hmm.
Tak boleh ke doktor?
I rasa the only option I kena tutup bilik Akashah dengan ni, lepas tu dia automatically akan masuk di sini dan jumpa you. Sekejap, I bagi tahu mereka.
Oops. Ooh.
Okay, kamu dah jumpa dah Syafiqah. Syafiqah, kamu dah jumpa dah Syafiq dengan Akashah. So you can
Oh,
continue here.
Okey doktor.
Hai Syafiqah. Lama asal lain slow. Equation of flow system. Oh, so this is the one sort reaction. Ooh. Hydroxide. Ah, example 3-2. Yeah. Lama asasnya.
Dia kat bawah tu Slide nombor 1
61 lah.
61.
Ha. Ada
Dia ada
jawapan.
bagi nilai kan?
Ha, betul. Sodium hydroxide tu limiting. Masuk yang table tu. Tak. Table tu construct macam mana? Aduh.
Table ni, Walid, table ni masa-masa kita diploma dulu kan, ada untuk table ni. Kita pernah buat dulu kan.
Syafiqah pernah buat?
Salah,
Wow.
Kita yang pernah buat tapi biasa weh. Itu diploma.
Ya, dah tak ingat saya. Dah tak ingat saya ada nak masukkan ni.
Tahun bila tu?
Masa lah korang?
Limiting reactant tu bukan ni glycerol sebab dia
Sebab dia
2 mol je. So dia lagi sikit.
Alah, bukan 20 lah. Aduh, rabun sangat.
Dia 20 lah. 2 kan?
Jap. Haa lah 2. Haa, yang tu. So yang tu limiting reactant. Lepas tu?
So buat macam table biasa lah. Kan?
Haa, table tu. Lepas tu table tu isi macam mana?
Formula
Initially,
lah kot.
ni.
Buat macam table 47 lah.
Ada seorang lagi masuk. Umaira.
Maira.
Ke Iman ni? Umaira.
Dia orang panggil dia Iman.
Oh, Iman. Alah, comel nama. Hai Iman. Jap. Oh, maksudnya just masuk formula lah ni kan?
Tu lah sebab tak ada nilai kan?
Adalah, X ada kan?
Dia punya tu kan, apa tu?
Ha?
Macam sekejap. Masuk balik.
Allah, gila saya. Boleh try present lah.
Kalau depends. Kalau kita ikut yang table tu kan, contoh macam yang A kita ni yang ketiga dah kan dia punya limiting reactant kan.
Limiting reactant dia yang so dia
B over A, C over A, D over A.
yang over A tu, yang tu untuk apa?
Macam dalam ya, table 47 kan. Itu B over A. So B kita tadi tu 1/3.
Betul, 1/3.
Masukkan kan, dia dalam tu macam tu kan.
Syafiqah cakap tak jelas lah.
Pakai earphone weh.
Kau pakai earphone lah.
Kau macam mumbling seorang tu.
Betul.
Sekarang. Sekarang dengar tak?
Dengar sedap. Okay, so lepas buat tu, aku try share screen tapi tak dapat. Kita stop.
Basically benda ni kena kira ke? Atau kita kena buat table tu je?
Table tu perlu isi data kan? Data tu yang perlu kira.
Oh, dia suruh ni lah. What is the concentration of glycerin when in AOH 20%?
X dah ada dah. Sekarang ni kita just kira yang C, A, C segala macam C ni dengan yang theta B tu dulu.
Ikut. Concentration tu lah.
Betul.
Yang dia bagi tepi tu.
Dengan theta bawah tu. Concentration tu kira macam mana.
Stop recording lah. Sebab sekarang tak ada
kan?
lagi.
Aku stop jap. Stop.